Hello, everyone. I'm Leslie from University of Maryland. Today, I will introduce our work Tidal, which is about tackling concept drift in provenance-based advanced persistent threats detection. And adverse persistent threats, or you can call it APT, are now causing a lot of damage across different countries. Here is how APT is affecting your system and how is it different from other attacks. So first, it will try to get access to your system through some phishing emails or infected files that let hackers to introduce malware. Second, when the malware is up and running, the hackers will try to remain undetected in your system. And third, the hackers will also search for some opportunities to gain administrator rights. And fourth, it will also move in your system. So hackers can tap into other services, or it can dig into deeper corners in your system. And fifth, importantly, it's persist, means that hacker can remain in place until they're achieved attack goal quietly. So the main difference here is APTs, they usually involve some advanced planning, and it often have human guided in the backend. And the attack can be multi-step or multi-stage. And also, more importantly, that it's persistent over long term in your system. And most of the existing APT detection systems, they are based on this provenance-based intrusion detection. So you will have the audit log from your system, and this audit log on the left side, it has some semantic information that indicates you what's the event and what is happening. Then from the log, you can also derive a provenance graph. And this graph will tell you how the data is flowing and how the attack is traced based on different system nodes. And with these PIDS systems, the APT detection can be in generally categorized into rule-based or learning-based methods. Today, we will only focus on the learning-based methods. And within the learning-based, at a high level, there are two types. So first, it can be anomaly-based, means that your system is trying to capture the normal behavior that happened in the system log. So whatever come in the future that deviated from your normal behavior, we mark it as anomaly. And the second type is signature-based, means that your detection system is trying to learn the attack signature or attack pattern of the previous APTs. So in the future, when there is a new attack coming that's very similar or same as your previous attack, the detection system will capture it. However, with all these learning-based methods, they all share one same assumption in their evaluation, which is they actually split a single attack data set for both training and testing. And this is a problem in APT because APT can really adapt over time. So for example, with an attacker that designed attack model 1, after it's deployed in your system, over time, it may be detected and blocked by security analysts. But after the hacker find it out, it will go back to adapt the old attack model 2 and redeploy to your system. And then your system becomes vulnerable again if you cannot adapt. And this is called the concept drift issue. And concept drift is not a new issue, of course. It already happened in machine learning or even in our networking field. And people are using this classical term or technology called transfer learning, try to address the concept drift issue. And transfer learning, one classical way is to just fine-tune a model on the drifted data or the newer data to have better detection. However, we test existing approaches with traditional concept drift solutions like fine-tuning, and we find out that they're still struggling with the concept drift issue. So here is one example with a signature-based detection method. First, so we're trying to capture the precision and recall, and we try to train and test this model on different settings. So here we use two different data sets, and they're both from DARPA. The first one is called E3, and the second one called E5. So they are from different years of the DARPA sources. You can see that the first group of the bar, that when your model is trained on E3, but tested on E5, which is the new data, the model performs really bad. However, if you continuously train this model or fine-tune it on the E5 dataset, and then when you test it on E5, the performance increase at the middle side bars. And then if you look at the right side bars, that after you fine-tune your model on E5, now if you go back to test this model on your E3 datasets, the performance dropped significantly. So this means that this classical fine-tuning approach, they're actually overfitting on the newest attack so that it will not be generalizable. So here is one insight we find out from the existing DARPA, public DARPA dataset. So here, as I was showing that there are E3 dataset and E5 dataset, and each of the column is a different attack type. So you can see that in terms of attack type, the APTs among different time, they actually share very similar patterns. For example, the first and second attack, they're both about some backdoor attack, like across E3 and E5. But however, if you look at their provenance graph, their graph embedding similarity can be quite low. So this means that the APTs among different time, although they may share some similar patterns underneath, they still have significant attack detail differences. And the existing fine-tuning technique, they are heavily overfitting on this, whatever the newest graph is, and that's why they were failing with concept drift. And here we propose to use this new architecture from the machine learning world, which is called multi-head transformer. And the key idea here is in this transformer structure, instead of fine-tuning every layer of this model, we have some shared layers that are trying to capture the common knowledge in your attack. And afterwards, when we fine-tune, we have this task-specific layers, which is a different head layer for every attack. Then when we fine-tune on these task-specific layers, it can better adapt to the newest attack without overfitting or forgetting the previous knowledge. And here is the workflow of Tidal. Let's say at timestamp 0, before the concept drift is happening, we first want to do data embedding. And here we want to extract the semantic information and also the graph structure information to form them as the model input. Afterwards, we do knowledge sharing by pre-training this base multi-head transformer model. And then at timestamp T1, when the concept drift happened, we then use the newest data after data embedding to fine-tune this multi-head transformer model. And here, importantly, we create a new head to fine-tune on this attack for the transfer learn. And then in the end, when the new logs are coming at the detection stage, the fine-tuned model will be deployed and tell you what's the anomaly detection results. And this is the end-to-end example of how the Tidal's detection results will look like. Let's say when you have some streaming audit logs coming, and after you deploy the fine-tuned model, that the model find out that here are a few lines of the log that seems like an APT attack. And afterwards, Tidal can help you construct this provenance graph, based on the attack nodes. And more importantly, that if you look at the graph here, Tidal provides some insights or intuition in terms of the relevance of the attack. So it will mark every node that are more likely to be related to the graph or to the attack, so that it gives the operators more information of what is this attack about and how is it happening. So for the relevance score here, we are calculating it based on some attention score that we get from the transformer model. And if you're interested in more details, please check our paper's design. Here, I'm going to introduce our evaluation setup. So as I mentioned that we are simulating the concept drift scenario based on the DARPA dataset from E3 to E5, and they're across a few years. And for E3 and E5 data, we try to create these different settings for concept drift. So first, we have the pre-drift setting, which means you simply train on E3 and also test on E3. And then we simulate when the drift happens. So when the E5 attack is coming, we then fine-tune the model on E5, and then we test it on E5 to see the post-drift performance. And then in the end, we also want to check if the post-drift model actually forget the previous knowledge. So with the fine-tuned model on E5, then we also want to test it on the original E3 data we have to see the performance. And for all of these settings, we run them on both Tidal and 4 baseline systems, include both the signature-based and anomaly-based. And here are our first key results. So we want to check the effectiveness of the knowledge transferring. And here in this graph, the first graph is about precision and second graph is about recall. And the setting is after we train it on E3 and then fine-tune it on E5. And when we test on E5, how's the performance look like? So you can see that Tidal, which is the highest straight line, that it has much better precision and recall than the baselines. Also, especially when the data is limited. So if you look at the x-axis, when we assume that the post-drift available data is gradually increasing, let's say from 10%, then at 10%, Tidal looks much better than the baselines. So it adapted much more effectively. And the second key result here is we also want to check if these different fine-tuned methods forget the previous knowledge. So if you look at the table on the left here, which is trained on E3 and test on E3, then every model's performance looks pretty good. It's around 1.0. However, if you look at the right side, which we check the fine-tuned model on E5, but then we go back to test on E3, what happened is all the baselines performance suddenly dropped a lot, but Tidal is still remains effective. So this experiment means that with the knowledge sharing and specific like adaptation of Tidal, Tidal is forgetting the least compared to the previous methods. And here I also want to raise some discussion points with you. That first, the Tidal's evaluation for concept drift is not the perfect because we in general really have limited data for the APT problem. And if you look at the previous paper, everyone is using this DARPA E3 and E5 dataset. So one challenge and important thing we can do in the future is to cooperate with industry to have more specific APT datasets that we can use to evaluate the concept drift scenario. And second, Tidal definitely has limitations. As I mentioned, that Tidal is based on learning the common knowledge and then try to adapt specifically to every single attack. That means it may not adapt well to the zero-day attack that has zero similarity with previous attacks. So for this kind of scenario, you might need some like better or newer detection system. And last, that the concept drift issue, it has happened in networking domain too. So for example, with learning-based methods in congestion control or in ABR problem in video streaming, that we all see the concept drift issue and we have discussed about it. So one open question here is, will Tidal structure also be a good fit for this kind of issue? That would be an interesting next step for us to try. And thank you very much for listening to the presentation.